So in the feedback on the Blackboard test, quite a few of you actually asked about the maths rearrangements, rearranging equations, which was in the video podcast for lecture 2. And I didn't have a chance to go over these in the timetable session, so I would just want to quickly go through these now. So the first was using the expressions for the rotational energy equals a half I omega squared, and the angular momentum P equals I omega, and we wanted to show that the angular momentum P equals square root of 2 e rot times I. So this is just basically some rearrangements, some rearranging equations, but I'll go through this with you. So if we have these two equations and we want to get rid of the omega, we can now rearrange this first equation to get an expression for omega. So if you rearrange this, we get omega squared equals 2 times e rot divided by I. So therefore we have that omega is equal to the square root of 2 e rot upon I. Hopefully that's clear for everyone. What we can now do is just substitute this expression in here, so we get P equals I multiplied by square root of 2 e rot over I. Now, what we can do is take this I inside the square root sign, and if we do that, we'll need to square it, because so the square root of I squared is I, so that's what we want here. So we can rewrite this square root of 2 e rot I squared upon I. And now if we just cancel out the I squared and the I, we get what we wanted. So P, the angular momentum, equals the square root of 2 e rot times I. So that was the first rearranging task I set you to do. So let's get rid of that. Okay, the second one that I set you to do was showing you that the transition wave number, nu tilde, in rotational spectroscopy, in general, so is F, the rotational term of the upper state, J plus 1, minus F of J. And I asked you to show that this can be written in general as 2b J plus 1. Okay, so to show this, we first need to know what F of J and F of J plus 1 are. So F of J, we should know, is B J plus 1. F of J plus 1, well, here J is 1 larger than it is here, so what we get now is F, so we get B, instead of J is 1 larger, so we have J plus 1, multiplied by J being 1 larger, so J plus 1 plus 1. So we now get B J plus 1 J plus 2 minus B J plus 1. What we need to do now is we can take out J plus 1 as a factor. So we'll take out J plus 1, and that leaves us inside B J plus 2 minus B J. If we now expand this, we get J plus 1 Bj plus 2b minus bj. These two cancel out, and this gives us our final this gives us our final expression to be j plus 1 as we required. So that's the second one I wanted to go through with you. So let's get rid of that now. So the final thing I wanted to go through with you was a bit of maths to show how you can calculate the value of j for which the maximum is observed in the rotational spectrum. So you'll remember that a rotational spectrum looks a bit like this. So we have intensity against energy, wave numbers. What we observe is a series of more or less equally spaced lines, and at some point here there is a maximum. So we need to be able to do a bit of maths to show for which value of j this maximum occurs. So the starting equation for this is the Boltzmann equation, including the degeneracy, because that's what determines where this maximum occurs. So this equation, we have nj over n0 equals gj over g0 exponential minus delta E upon kt. So we've discussed all these terms in detail in the lecture, so I won't go into that in any more detail now. What we want to do is just substitute the appropriate values for rotational spectroscopy. So here we go. So nj upon n0 is equal to 2j plus 1 upon 1 exponential minus bhc j plus 1 upon kt. So that's the equation we need to work with in order to find out where this maximum occurs. What I'm going to do now is make a bit of space on the board, and then we can start thinking about how we're going to do this. So, if we have a maximum in a curve, the maximum is a point where the gradient is 0, so the differential of the function is equal to 0. So what we can do is take the differential of this function, set it to 0, and find out the value of j for which this is 0. So we need to work with this rather complicated expression and do a bit of differentiation. The first thing you normally do when you have an expression like this, which involves exponentials, is to take logs, because then logs allow us to get rid of the exponentials. So what I'm going to do now is take the log of that. So the log of the left-hand side gives us log of nj minus log of n0. This is why there are log questions in the maths workshop earlier this week, to practice this sort of thing. We can now take the log of this thing here, and this gives us log of 2j plus 1. And then we can take the log of this thing here. So the log of exponential to minus something is going to be minus bhc j plus 1 upon kt. So this is just taking the log of this expression. So it's just practicing taking logs. Let's get rid of that, we don't need that anymore. What we can do now is work with this expression. So what we want to do is differentiate this expression with respect to j, because we want to find out the value of j for which the gradient is 0, so this is effectively where the maximum occurs in the rotational spectrum. So what we want to do now is differentiate this whole thing with respect to j, and this gives us d log nj dj minus 0, because this is a constant. So if you differentiate a constant with respect to a variable, you just get 0. Now, if we want to differentiate log of something, what we get is 1 over the something multiplied by the differential of what was in these brackets here. So 2j plus 1 differentiated with respect to j gives us 2. So that's this first term differentiated. This next term is a little bit more complicated, but then if we can expand these brackets here, we end up with minus bhc j squared plus j upon kt. So we can see what we have here is a constant factor in front, and we need to differentiate j squared plus j with respect to j. So we end up with minus BHC on KT, just the constant bit. J squared differentiated with respect to j gives us 2j. J differentiated with respect to j gives us 1. So we end up with 2j plus 1. Okay, so now we've got this expression here. What we need to do is set this equal to 0, because where d log nj dj has a maximum, where log of nj has a maximum, the derivative with respect to j is equal to 0. So this whole left-hand side is equal to 0. So now we have 0 equals 2j plus 1 minus BHC on KT, 2j plus 1. So now we just need to rearrange this and get in the end get an expression j equals. So again, let's make a bit more space. So what we want to do is gather all the terms in j on one side of the equals sign. So let's start off by just bringing this across to this side. So we end up with BHC on KT, 2j plus 1 equals 2 over 2j plus 1. Now I can get rid of this, give me even more space. So what we do now is just rearranging. So what we can do is we want all the j's on one side. So you can see you've got 2j plus 1 here and a 2j plus 1 here. So if you multiply both sides by 2j plus 1, we'll get 2j plus 1 squared equals 2. So 2j plus 1 has gone from here to here. BHC upon KT. Now we can multiply both sides by KT, and so that moves across here, and divide both sides by BHC, so this goes from here down here, and we end up with 2j plus 1 squared equals 2KT upon BHC. Now, we've still got squares here, so we want to get rid of that, so we'll just square root both sides. So 2j plus 1 equals the square root of 2kt over BHC. Now we're almost there, so again just need to make a bit more space. So we can now subtract 1 from both sides, divide both sides by 2, and we'll end up with j equals a half of square root 2kt over BHC minus 1. So this is what we've got in the lecture notes. So we've shown now actually how to get this value. What we can do now is actually put in numbers. So if we take the molecule of carbon monoxide, for example, so if you say carbon monoxide, we know what the value, we can work out what B is for carbon dioxide, or we can look it up. If you say, and it's take 200 Kelvin, then if you just substitute numbers into here, we'll end up with J is approximately equal to 6. Now, you'll end up getting 5 point something or 6 point something, but you have to remember J is a quantum number, so it has to be an integer. So the closest J to the number we get is 6. So J max. So the value of J for which the population is largest is 6 for carbon monoxide at 200 Kelvin.